Welcome to Biochemistry Simplified. Glowing star, in today's video, we're diving into the fascinating world of bioenergetics, the science behind how our cells produce and use energy to power life. Stay tuned as we break it down step by step, making complex concepts simple and easy to understand. Don't forget to hit subscribe for more engaging biochemistry insights. Let's get started.
Hello, welcome to Biochemistry Simplified. Good day, good morning, good afternoon, wherever your time is. We are going to start today our discussion on a profoundly important topic known as the bioenergetics, which is the energy transfer that takes place in biological systems. Today we are going to be discussing the thermodynamics, free energy, and equilibrium. I cannot overemphasize or overestimate how important this topic is. If you do not walk away with anything else from this topic or course, an understanding of bioenergetics will serve you for many years to come, particularly those that goes on to graduate schools looking for research careers. Understanding what is happening energetically will allow you to understand pretty much everything that is happening and needed. So let's just get started. But before I begin, I want to quickly say that the problems and exercises we'll be looking at as regards this course will be done during the teaching towards the end of the teaching or lessons, such that it will be in a series of lessons, and the problems and exercises will be done one after the other. If there's something that is not exactly clear from this first class, please don't worry. We will actually do the problems, and it is a great way to consolidate with a whole lot of exercises and problems at the end of the topic or class. That gives us a chance to also review all that we would have done as we do the problems. So let's get started with the reaction. So today we'll be looking at the reaction. Let me get my pen. All right, let me take red. Okay. So we'll be looking at the reaction that is going on with glucose. So we want to look at glucose. Reaction with glucose and inorganic phosphate. And of course that gives you glucose 6 phosphate. So it gives you glucose 6 phosphate, and the glucose 6 phosphate will represent that structurally here as follows. So we have the glucose 6 phosphate represented here. So we have OH here. We have another OH. This is OH going up. And here we have CH2 OH. And of course, this is the glucose plus the inorganic phosphate. So the inorganic phosphate, we have the phosphate group, which is OH, double bond O, O minus, and O minus. So that's the phosphate, and that reacting together gives you the glucose 6 phosphate that is structurally represented here. So we have OH here. This is also another OH. And we have OH. We have OH. And we have CH2 O, double bonds, double bond O, O minus, and of course O minus. So this is glucose 6 phosphate, and that simply shows the structural representation. This happens to be the very first reaction of glycolysis, and this is a reaction that we definitely want to move forward. It is very important that this reaction moves forward and moves forward easily. But just because the reaction wants to move forward, so because the reaction wants to move forward does not mean just writing this equation like this does not mean that it happens. In discussing thermodynamics, we speak of spontaneous processes, more specifically spontaneous reactions. That is in fact very important to note. So we say just because we write an equation like the way we have done now, just because we write an equation does not mean that it happens, does not mean that it happens. So in discussing thermodynamics, we speak of spontaneous process. We speak of spontaneous process. We speak of spontaneous process or processes, more specifically we are actually looking at what? Spontaneous reactions. Spontaneous reactions. Yes, that is it. So just because we write this equation of glucose plus inorganic phosphate does not mean that it happens. So when we are looking at thermodynamics, we are actually speaking of spontaneous processes, and more specifically we are looking at spontaneous reactions. So now Spontaneous does not have the same meaning as is used in our normal daily speech. So what is spontaneous? Spontaneous means, okay, let me do that in the next page. Okay, so spontaneous means that it wants to happen naturally, and if circumstances are right, it does happen naturally and easily without external pressure. That is, thermodynamically speaking, spontaneous means it wants to happen. It wants to happen naturally, right? And if the circumstances are right, it does happen. Sorry about that. The circumstances are right, it does happen naturally. It does happen naturally and easily too. It does happen naturally and easily without external pressure. Without external pressure. So that's what's spontaneous. So when we talk about spontaneous reactions, we are making a thermodynamic statement. We are actually saying that the reaction wants to happen, all things being equal, and if the reaction actually happens or starts, if the reaction actually starts and the circumstances are good for it to happen, okay, it actually wants to happen. If the reaction starts happening and the circumstances are good for it to happen, it will happen without us doing anything about it. So the spontaneous does not refer to speed as it were. It does not talk about how fast this reaction is going to take place. That actually falls under the domain of kinetics. Thermodynamics just speaks about the potential for something to happen, the extent to which it wants to happen, while kinetics is the domain that discusses whether we can make it happen and how fast we can make it. So in any reaction, let me do this in another color. Okay. So in any reaction, nature actually wants to do two things in any chemical reaction, any reaction at all, biological reaction, biochemical reaction. Nature actually wants to do two things. And what are they? So in any reaction, in any reaction, in any reaction, sorry about that, in any reaction, nature wants to do two things. Nature wants to do two things. So one of them is in going from reactants to products. So the number one of those things nature wants to do is in going from reactants to products. A reaction wants to release heat. A reaction wants to release heat. A reaction wants to release heat. That is, under normal ideal circumstances, any kind of reaction actually wants to release heat naturally. And in this case, you talk about the enthalpy of the reaction. So as such, the enthalpy, which is delta H of the reaction, is the quantitative measure. So you talk about the enthalpy, which is delta H of the reaction. So the sorry about this. It should be. Let me remove this from here. So we have the enthalpy of the reaction, and what that implies is that the delta H of the reaction, okay, the delta H of the reaction is the quantitative measure of this tendency at constant pressure. Is the quantitative measure of this tendency at constant pressure. Constant pressure. So that is it. So enthalpy, which is delta H, is actually the quantitative measure of the release or the gain of heat in a reaction. But this is actually under ideal situation, because under ideal situation the reaction wants to release heat. So we look at the number two thing any reaction wants to do. We look at number one, which is reactions going from reactants to products a reaction always wants to release heat under ideal condition, and that speaks of the enthalpy of the reaction. That speaks of the enthalpy of the reaction. So right now we want to now look at the point number 2. The reaction wants to become more disordered. The reaction wants to become more disordered. Why is this so? Things fall apart. Things do not go from a state of disorder to order without some external help, but things will naturally go from a state of order to disorder without any input or external force. That is the nature of the universe. That is how it works. And that is actually the second law of thermodynamics, which speaks of the entropy. That is, the entropy always increases. The entropy always increases in a natural process. Under ideal conditions, reactions would like to become more disordered as it moves from reactants to products. That actually favors the forward movement of the reaction. It wants to become more disordered. So in this second point, we are actually looking at what? The entropy, which is the delta S of the reaction. The delta X of the reaction, which is the entropy of the reaction. And the entropy of the reaction shows that the quantitative measure of this tendency. What tendency? Of the reaction to become more disordered. So the entropy is the quantitative measure of this tendency. Is the quantitative measure of this tendency. So we'll begin to look at what happens to these two important points of how a reaction behaves, always wanting to release heat, talking about the enthalpy, and always wanting to become disordered. We want to look at different conditions and how they behave under the following conditions. So we'll look at that quickly, the different conditions in which they behave. Let me do this in red. So the different conditions and how they behave. So we'll say in the following conditions, we are actually looking at how the enthalpy, delta H or delta X, the entropy, behaves. So in the following conditions, one of them is when the delta H is what? Less than 0. When delta H is less than 0, what happens is it releases heat. It releases heat. Okay, and that actually depicts an ideal condition. So we said at all normal ideal condition, the reaction wants to what? Release heat and that's how the reaction moves forward. Because it wants to move forward, it will release heat under ideal condition. So the next point we want to look at is when the delta H is greater than 0, what happens is that it requires heat. It requires heat. That is, or it absorbs heat from its surroundings. It absorbs heat from its surroundings. So this situation is actually referred to what? Less than an ideal condition. Less than ideal condition. Okay, so that's for the enthalpy of the reaction. So what about the entropy that always wants to become disordered? That's talking about the delta S. So when the delta S, sorry about that. Okay, so when the delta S is greater than 0, okay, when the delta S is greater than 0, what it implies is that the disorder increases, and that is in ideal condition. Disorder increases. And that shows the disorder increases in what? Ideal conditions. Okay, so when the delta S, okay, and I still do it here, and the delta S is, okay, sorry, let me just take that to the next page. So now we'll see delta S greater than 0, disorder increases. In the next page, when the delta S is what? Less than 0, what it implies is that the disorder decreases. The disorder decreases, and that shows less than ideal conditions. Sorry about that. Less than ideal conditions. Yes. Alright. So we've seen the different conditions in which entropy and enthalpy, how they behave. When the delta H is less than 0, it releases heat, which is ideal conditions. Greater than 0, it requires heat, or it absorbs heat from its surrounding, which is what? Less than ideal conditions. While for the entropy, when it's greater than 0, disorder increases what? In ideal conditions, and when it's less than 0, disorder actually decreases, which is less than ideal conditions. Okay, so these two properties, enthalpy and entropy, that is delta H and delta S, plus a third party which is temperature, they actually contribute, combine, and compete in such a way as to give rise to a single number that tells us whether a reaction wants to move forward or not, want to move forward naturally or not. So these two properties, let me do this now in black. Okay. So these two properties, worthy of note, these two properties, which is the enthalpy, and the entropy, which is the delta H and the delta X, and the delta X plus a third property, that is the temperature. Temperature. These three of them, they actually combine. The three of them, they actually contribute. They contribute they combine, and compete. They contribute, combine, and compete in such a way as to give rise to a single number, that tells us whether a reaction wants to and can move forward naturally. Okay, so that tells us whether a reaction wants to, and can move forward, naturally. That is it. That single number they give rise to or generate is actually the what? Delta G. The delta G. That number is actually what? The delta G. So I'll take this. That number is delta G, and we want to see, let me do this in red. We want to see the delta G now. The delta G, that number which is delta G, you have here the delta G. So thus delta G, which is actually the number, okay, delta G is equal to delta H minus temperature delta S. Okay, delta G equals delta H minus temperature delta X. This is profoundly important relationship equation in thermodynamics. This is a very important relationship equation. A very important equation in what? Thermodynamics. In thermodynamics. So that is it. Let me write this word again. So in thermodynamics, I think I'm writing too big these days. Yes, that is it. In thermodynamics. So if I have a reaction, I can actually measure the change in the reaction by measuring the change in the enthalpy, which is delta H, and the change in the entropy, which is delta X, at a given temperature. These three things, which is the enthalpy, the entropy, and the temperature, actually combines, and we can have this combination with the Gibbs free energy, which is what? Delta H. The Gibbs free energy, it is a single number that tells us whether the reaction will move forward spontaneously under ideal conditions, that is, under the right circumstances, or whether it will not or it cannot. And if it cannot, we will have to do something to make it happen. So that number is what? The Gibbs free energy. So delta G here is the Gibbs free energy. So where delta G implies what? The Gibbs free energy. Of course, delta H is the enthalpy. The H is the enthalpy. Delta S is the entropy, and of course T implies what? Temperature. So that is it. So we've seen a very important relationship equation in thermodynamics. So of course this should be at what? Constant pressure. So this equation, very important in thermodynamics, and should be at constant pressure. Okay, so this should be at constant pressure. Of course, this should be at constant pressure. Very important to note that. At constant pressure under what? Physiological conditions. This should be at constant pressure under physiological conditions. So I think forward naturally. Okay. So under physiological conditions. Great. So important, this relationship. So in our next page, we'll begin to look at how this relationship works. So, of course, we said this delta G in our previous relationship. Let me just put it down here. The delta G is equal to delta H minus C delta S. So here where delta G is called what? It's called the Gibbs free energy as earlier established. Here delta G is called the Gibbs free energy as earlier established. Okay, delta G is called the Gibbs free energy. Sorry, deleted my energy. The delta G is called the Gibbs free energy. Okay, as written. Okay, so when you say and it tells us if a reaction as written, that is thermodynamically favorable. So this delta G tells us if a reaction is thermodynamically favorable. So it's called delta G, and it tells us okay, it tells us if a reaction is thermodynamically favorable. Tell us if a reaction is thermodynamically favorable. As written. So when we say as written in thermodynamics, it means if the reactants from reactants to product, that means the reaction is going from reactants to product or from left to right. Now, this relationship does not tell us that it is going to happen. It only tells us that it is favorable, or whether it is favorable or not. And with all things being equal, it will happen. It does not say about how fast or how it does happen. If I put hydrogen and oxygen into a tank, for example, there will be no reaction. The hydrogen and the oxygen are not going to combine to form water. Thermodynamics says except they really want to do so, they really are interested in doing so on their own, and not because I want them to form water. For it to become thermodynamically favorable, I have to ignite it with a spark, that is, put a little bit of energy into it, just to get it over the hump. That hump is actually referred to as what? The activation energy. Then everything will be fine. The reaction will sustain itself, and it will go very far forward and release a lot of energy, which is what? The enthalpy. But it does not mean it is going to happen so. This thermodynamics just speaks about this tendency for it to happen. So that is basically what it is. So following the conditions, this delta G, when delta G, like we saw with delta H and delta S, when delta G here is less than 0, what it implies is that it is what? Negative delta G. It is negative delta G. And what that implies is that it is favorable. It is favorable. It will happen naturally. It will happen naturally. And it will also, it is favorable. Favorable. It will happen naturally. And it will also happen spontaneously. So that's what negative delta G is. It's favorable, happens naturally, and it will happen what? Spontaneously. However, when the delta G is greater than 0, what this implies is that it is not favorable. Of course, maybe positive. It is not favorable. It is not favorable. It is spontaneous in the reverse. It is spontaneous. It's spontaneous in the reverse. It is spontaneous in the reverse. So we've established a whole lot of things today about the thermodynamics and spontaneous reaction, the two things that happen in nature. The reaction always wants to release heat under ideal condition, and it always wants to be disordered, which speaks of the entropy and the what? Enthalpy. And we saw a very, very important relationship in thermodynamics at constant pressure under physiological conditions, where you have what? The introduction of the Gibbs free energy, which of course the enthalpy and the entropy with the temperature combines to give a particular number, and we said that that number is what? Your delta G, which is the Gibbs free energy. And that Gibbs free energy tells you if a reaction as written is what? Thermodynamically favorable. And when we say as written, it simply implies that the reactants is proceeding to products. The reaction is moving from left to right. Great. In our next set of lectures, we'll begin to look at the specific reference frame that is needed in this thermodynamics process.